My name is Rudder Gatto and my partner is Stephen Sharp. Our presentation is on the control of a thrust vector in CubeSat using a single variable speed control moment gyroscope. CubeSats should be small, light, cheap, and simple as possible. So we want to minimize the amount of thrusters and MEDs per CubeSat. Normally, full attitude control is impossible with just one MED and one thruster. For instance, you'd need 3 reaction wheels or CMGs for 6-axis control. For redundancy, 4 to 6 MEDs are commonly used. However, if we only need a 0.1 axis of the CubeSat in a certain direction and don't care about MED redundancy or spinning around that axis, then we can use a VSCMG for attitude control and a thruster for translations to perform orbital maneuvers with a minimum number of actuators. This configuration is valid if the control law reaches stability in a torque-free motion. Additionally, we can show that the system is robust by maintaining stability with perturbations and a thruster offsetted from the center of mass. We can also apply the control law to a rendezvous mission. For the dynamic theory, we assume a negligible gimbal acceleration, a time-varying spin rate, and a moment of inertia of the spacecraft being constant due to the time-varying moment of inertia of the CMG being much smaller. We can define the dynamics of the problem with the listed equation where U and D are control terms. M represents any disturbance on the spacecraft, which are considered for the case where the thruster is offsetted by the vector D. For the stability analysis, 3 control modes are analyzed. First, nonlinear reduced attitude control for thrust vectoring is asymptotically stable for states omega-1 and omega-2, while omega-3 stabilizes to a constant value. Next, nonlinear control for impulsive thrust vectoring is asymptotically stable for states omega-1 and omega-2 and the pointing error gamma e, while omega-3 is not guaranteed to convert to 0, the pointing direction is invariant to changes in omega-3. Lastly, nonlinear tracking for low thrust continuous vectoring is asymptotically stable for omega e star and gamma e. However, the third component of omega e does not convert to a constant value like the pointing control maneuvers. For the simulation, we implemented 3 Simulink models, the top being the dynamics for the VSCMG, bottom left being the repointing maneuver, bottom right being the tracking maneuver. These are the simulation parameters we use. Everything is a constant between the simulation maneuvers, however, the desired pointing direction changes along with the gains. Within the first 5 seconds of the repointing maneuver, the spacecraft's rotation is driven towards the desired attitude due to angular velocity spikes as the VSCMG spins up. The wheel reverses spin direction several times while continuing to gimbal in a single direction, taking about 5 seconds to flip the VSCMG around by 180 degrees. Our attitude results follow similar trends to the paper, but a discrepancy occurs after the pointing error reaches 0, causing the attitude error to oscillate around the equilibrium point by about 0.02 in each of the x and y directions. However, the angular velocity is asymptotically stable for omega-1 and omega-2 and stable for omega-3 as expected within the paper. While the wheel's spin rate remains constant, the VSCMG continues to gimbal at a constant rate of about -0.1 radians per second. Therefore, it is likely that stopping the rotation of the gimbal would allow the spacecraft's pointing direction to reach equilibrium.
Moving on to the results of the tracking simulation, we can see that the overall goal of following the desired moving attitude is achieved, as the pointing direction error is driven towards 0. However, our results exhibit the same oscillatory behavior as the long-term repointing results. The pointing direction error also oscillates in the author's results. However, the oscillations there are reduced much more rapidly than in our results, and the errors in each of the 2 axes are not as closely related. Note that the plot labeling on this slide can be confusing, as gamma E1 is actually the pointing direction for this simulation as opposed to the third axis being referred to in the dynamic theory, but the results will be unaffected and we have left the labels as they appear in the paper for consistency. Conversely to the attitude error, our angular velocity is minimized far more quickly than in the paper. Omega-1 still reaches a value of -0.2 radians per second, which is exactly the rate at which the desired attitude is rotating, so our goal is achieved there. The difference in the sign of omega-1 between our results and the papers is presumably due to the authors adopting a positive value for clockwise rotation, whereas our standard is to denote counterclockwise rotations as positive. The spin rate and gimbal angle show the greatest discrepancy when compared to the paper's results. Both reach a steady value within about 2 minutes of our simulation, but take over 6 minutes to do the same in the paper. The final spin rate is also much different, with our VSCMG reaching a spin rate of about 12 radians per second, which is almost 2 full revolutions each second. More research is definitely necessary to determine whether this would saturate the CMG or not. Thankfully, the final gimbal angle approaches 0 in both simulations. The paper also presents the steady state behavior of the VSCMG at the end of the tracking simulation for our comparison. Note that the authors incorrectly labeled this plot as omega 3 when it is in fact representing omega 1. The absolute value of the angular velocity is the same, neglecting the previously mentioned sign change, and the scale of the deviations is just slightly smaller in our simulation than in the paper. Although the period is different and the amplitude of our angular velocity oscillations are more consistent than in the paper. The large discrepancy in the final spin rate is even more apparent in the steady state plots. Both the spin rate and gimbal angle show the exact same trends as the angular velocity at steady state, with our simulation showing consistent oscillations with a shorter period than the papers, although the amplitudes are very similar. In conclusion, we recommend not relying only on a single VSCMG for attitude control, as it has no redundancy, so a single malfunction in the CMG will take out the entire spacecraft's attitude control. Additionally, while it may use fewer momentum exchange devices than redundant configurations, the complexity of the internal components of the CMG far exceeds that of reaction wheels, even when there are 3 or 4 of them. The time required to reach steady state is also much longer than traditional momentum exchange devices, and even at steady state you only get control of 2 of the 3 axes, so any sensors or docking ports will have to be designed to accept the uncontrolled rotation about the pointing axis. Instead, we agree with the author's suggestion to use the VSCMG as a backup for other momentum exchange devices, as this allows the spacecraft to still maintain pointing even in the event of total failure of all the other MEDs, while avoiding all of the aforementioned disadvantages during nominal operation. In the future, we would like to implement the rendezvous and offset thruster simulations and add external disturbances into the existing simulations. However, certain errors noticed throughout the paper make it difficult to rectify our results with the authors, as we cannot guarantee that all of the equations presented in the paper are notated correctly. Therefore, any future research into this topic will require cross-checking with other publications. Thank you for watching our presentation.